Professor Raphael Ponge, and he will speak about semi-classical analysis and non-commutative geometry. So please start.
All right, so привет everybody. So I cannot see any, if somebody speak, but I cannot see the chat, so if there's some message in the chat, please let me know, because...
Yes, we will inform you if there is something.
Okay. So that, right. Okay, so this way. All right, so maybe I have to... All right, okay. Is it still good, or? Okay, so my talk, I would like to present links between two different parts of quantum theory. So on the one hand, non-commutative geometry, and on the other hand, classical analysis of, semi-classical analysis of Schrödinger operators. So now what I want to do, sorry, okay, maybe I put full screen. So I put on full screen. Okay. So the main result is a semi-classical Weyl law in non-commutative geometry. And this has applications, so I also mentioned some several applications in semi-classical analysis and non-commutative geometry. And all this has its roots on the one hand from the operator theory approach to semi-classical analysis, pioneered by Biermann, Solomiak, and Simon, and on the other hand, by the role of operator ideals in NCG. So semi-classical analysis, so semi-classical Weyl law. So I will present the version on Rn. So notation I'm going to use throughout the talk is that n minus h is a number of negative eigenvalue, where h is a self-adjoint operator which has discrete negative spectrum. So for Schrödinger operator on Rn, they correspond to the operator delta plus v. So delta is a positive Laplacian. This corresponds to the number of bound states. And the semi-classical Weyl law states that, so if you look at if the v is well, so suppose that simplicity that v is a continuous real value potential. So look at the semi-classical Schrödinger operator, h square delta plus v, and the number of negative eigenvalue is like h to the n, where where the leading, well, with a coefficient which is an integral of the negative part of v to the n over 2. So we can also consider fractional Schrödinger operators. Okay, those the 2q with q plus v. Okay, and again the number of negative eigenvalue depends only on the negative part of v. So in non-commutative geometry, the Weyl roles of manifolds are spectral triples. So spectral triple, so this is an algebraic definition. So it consists of algebra A, it consists of Hilbert space H, a star subalgebra of L of H, and a self-adjoint operator D with compact resultant, which commute with element of A, modulo bounded operator. And I also say that spectral triple is B-summable if the eigenvalue of D inverse, the absolute value of D inverse, are like a big O of J to the minus 1 over P. So it means that the resultant is in the weak second class at P infinity. So so notation I will use throughout the talk for the eigenvalues is like lambda J. So here lambda 0. So here this is notation for the eigenvalues of absolute value of D minus 1. P-summability. Okay. P summability here implies that the prior trace of d to the minus q is finite for all q greater than p. And you can think of degree of summability as some kind of substitute for the notion of dimension. So you can think of degree of summability as the dimension of the spectral triple. So I give several examples of spectral triples. So first, consider a bounded domain with a smooth boundary in Rn, n greater than or equal to 2. So if consider the take the square root of the Dirichlet of Dirichlet or Neumann Laplacians, it's going to give a spectral triples where the Hilbert space is a space of L2 functions on omega, and as algebra you can consider the algebra of smooth function on omega with compact support. But since we also need a unital algebra, we can add the constant. Okay, so CC infinity omega plus C, this is a smooth function with compact support plus constant functions. So this is spectral triples. When you have a closed Riemannian manifold, so you can replace, you can take the square root of the Laplacians and take Hilbert space with a space of L2 function on M, and algebra A is algebra of smooth functions on M. So a more substantial, non-commutative geometry, more interesting, from point of view of non-commutative geometry, a more interesting example is when you replace the square root of delta G by the Dirac operator. In this case, Dirac operator acts on a spinor bundle, so the Hilbert space is a space of L2 spinor. But for this talk, this spectral triple is pretty good, actually. And all these spectral triple are n summable, and here n is the dimension of the underlying manifold or domain. So a semiclassical Weyl law in non-commutative geometry. So there was a result was obtained by to McDonald-Sukochev-Zanin in 2000. I think the paper was published last year. So work as follows. So consider a unital spectral triple AHD. Assume it is P summable. Again, it means that the eigenvalue of the resolvent are big O of J to the minus 1 over P. And denoted by A bar, the closure of A in LH. So for semiclassical Weyl law under 3 conditions. So the first condition is that P is greater than 2. So it means that we only so this means we work in dimension strictly greater than 2. We also had a called Lipschitz regularity. So in definition of spectral triple require a commutator of D with element of the algebra A to be bounded. And we require the same property for the absolute value of D. And we require also a Tauberian conditions. Namely, so for every positive element of A bar, we take the trace of A to the Z absolute value of D to the minus Z. So this is this operator is a trace class for a real part of Z greater than P because of thanks to the P summability. And so we take the trace, so it's a morphic function, and we assume that it has a meromorphic extension past the line real part of Z equal P with a single pole at P. Okay. And under this condition, we obtain a semiclassical Weyl law as follows. So for every self-adjoint element of A bar, if you look at the number of negative eigenvalue of H square D square plus V, multiply by H to the P, and as H goes to 0, it converges to this guy. So this is basically the value of this functional at A equals negative parts of V to the Randolph. Voilà. So we have several questions about this result. So first, we conjecture that the result continue to hold for P less than or equal to 2, but in order to that, we really have to use another approach. I mean, another question is, can we remove the Lipschitz regularity conditions? And a further question is, question was actually asked by Cohn during an online presentation of the result. And can replace the Tauberian condition by a more standard Tauberian condition. So let me briefly go back to this condition. So the issue is, so this is like a zeta function, which consider in spectral geometry and so in noncommutative geometry, except that often we don't put a to the z, we just put a only. So when a is a function, that's not much a big deal, I guess. However, it's probably a much more, it's a bigger deal if you would, for instance, let A be a pseudo-differential operators. Okay. So I'll go back to this. So we have like 3 questions, and in fact, the answer to all these questions is yes. So we have the following result. So suppose that AHD is a P-summable spectral triple, so P can be any positive number, and we assume that we have one of those 2 Tauberian conditions. So we can state it in terms of zeta functions or in terms of each trace asymptotic. So first condition states that if you take trace of A to the absolute value of D to the minus Z, it has a single pole at Z equal P, which denoted by tau of A. Okay. And or you can also require trace, look at the trace of the it semigroup, so trace of it minus TD squared. And require it as it's like you have a leading term, which is like t to the minus p over 2, denote the coefficient by 2 of a, and also assume that there is some remainder term. Okay, small remainder. So the second conditions imply the first conditions, and under this, but this condition are satisfied in many examples. Okay. So there are natural Tauberian conditions. And under this condition, first you have a Weyl law for some Biermann-Schwinger type operators, namely for every self-adjoint element of a bar, any Q positive. So you look at this Biermann-Schwinger operator, which is absolute value of D minus Q over 2A, absolute value of D minus Q over 2, is self-adjoint, and it's compact. So you can look at the positive and negative eigenvalue, and you get you have a semiclassical Weyl law for this. And you have a Weyl law for this positive and negative eigenvalue, which is given in terms of tau, and you take tau apply to some power of a positive or negative part of A, and raised to some power. So so lambda j plus minus are positive and negative eigenvalues. So why is it denoted by tau of A? So in science it is a notation, but often what you expect is that tau is given by the geometric data. For instance, in case of Dirac spectral triple, tau is given by integration against Riemannian volume. Okay. So that's given by geometric data. So you have this Weyl law for negative order pseudo-differential operators, I mean for Biermann-Schwinger operator. And so by the Biermann-Schwinger principle, this implies a semiclassical Weyl law. So namely for every self-adjoint element of a bar and for every Q positive, you have a Weyl law for the number of negative eigenvalue of h to the 2q, d to the 2q plus v. So it's like h to the p times h to the minus p, times tau of negative part of v to power p over 2q. And when q is equal to p, so you get j here. So basically it means you have a convergent operator here will be actually in the weak trace class. And by general result, this implies a trace theorem. That is for all normalized positive traces on L1 infinity. Phi of A to the D to the minus P is equal to tau of A. So in terms of non-commutative, from non-commutative geometric point of view, phi of A to the minus, so the positive traces on normalized positive traces on L1 infinities gives a non-commutative integral. So it basically shows that the non-commutative integral of A to the D to the minus P is equal to tau of A. Okay. For every A in the C star closure. Right. So, right, so now, supposed to finish at 14. All right, so now I give some, I will explain, give some example. So first I will explain how we can recover some already known result. in a case of Dirichlet. So first, in terms of the Dirichlet and Neumann problems. So consider a bounded domain with smooth boundary in Rn, unity omega. So delta is a positive Dirichlet or Neumann Laplacians. So you have a spectral triple using the square root of delta, where the algebra is CC infinity omega plus constant, and the space is equal to omega. And by result of, so to apply the main result, you need to get a short-time asymptotic or have a result about residue of zeta functions. So short-time asymptotic for the Dirichlet Neumann Laplacians goes back to a result of Karman and in Meenakshi Sundaram. So Karman is in dimension 2, and Meenakshi Sundaram is in late 40s. This is for any dimension, and it was proved in 1949. So for what you get is that for every continuous functions, trace of f to the t to the minus t is like t to the minus n over 2 times the integral of f plus remainder term. So you get the spectral triple and a short-time asymptotic, so you can apply the main result. And in this case, you recover the semiclassical Weyl law for the Dirichlet and Neumann-Schrödinger operators. So this was known at least from the 70s, maybe even earlier. So I said for continuous potential with real value continuous potential. So every real value continuous potentials on omega bar and every q positive cube, you get you have an asymptotic for the number of negative eigenvalues of s to the 2q delta q plus v. So it's given in terms of integral over omega of the negative part of v. So I should mention that this, many people here know this can be extended also to LP potential thanks to work in particular of Biermann, Soloniak, and Rosenblum. Right. So you recover the semiclassical Weyl law for Dirichlet and Neumann problems from the result of Karman and Meenakshi Sundaram, at least for continuous potentials. Okay. Now we have similar result for on a closed Riemannian manifold. So let Mg be a closed Riemannian manifold. Again, square root of the Laplacian gives spectral triples, whereas the algebra A here is algebra of smooth function. Right? So you also have a short-time asymptotics for the IT semigroup. So namely, which is due to Meenakshi, Sundaram, and Pleyel. So it's a very famous result. So they use this. This was probably one of the first proof of the Weyl law for Riemannian manifold, classical Weyl law. So the trace of f to the e to the minus tg, this is t to the minus n over 2 times the integral of f against the Riemannian measure plus a remainder term. So, okay, so you have a spectral triple, short-time asymptotic. So you can apply the semiclassical Weyl law in TG, presented before, and you recover semiclassical Weyl law on Riemannian manifold. So that is for every real valued functions on M and every q positive. You have an asymptotic for the number of negative eigenvalue of h to the 2q delta gq plus v. So it's like h to the minus n times the integral of the negative part of v to the n over 2q against the Riemannian way. Okay, so that's okay. So you see that's recover result. Semiclassical Weyl law from the result of famous result of Meenakshi, Sundaram, Pleyel from the late 40s. So let me remind you the main result. So the main result, so you get so you have semiclassical Weyl law, and this semiclassical Weyl law is deduced from Weyl law for some Biermann-Schwinger operators, and this Weyl law for Biermann-Schwinger operator also implies a trace theorem. So now you can do a variant of the previous example where you replace the algebra of smooth function by the algebra of pseudo-differential operators of order 0. So denote this algebra psi 0 of m, and denote by psi 0 of m bar the disclosure in L2 of m. So since it was denoted by, I think, by m in Yuri Kordukov talks. And observation is that if you replace the algebra of smooth function by the algebra of pseudo of order 0, you still get a spectral triple because this is going to commute at the level of principal symbols. Okay, so we take commutator of square root of delta g with a pseudo of order 0. This is a pseudo of order minus 1. No, sorry, it's a pseudo of order 0. Yeah, it's Friday night in China, so a bit exhausted. So commutator of pseudo of order 0 with a square root of the Laplacians is order 0, and it's bounded. Okay, so now what do we get right? And well, and here we have a result which goes back to Siles and well, I think at least to Guilmin and Wojcicki about the residue of zeta functions of form A delta G to the minus z over 2. Okay, so we have a residue at z equal n, which is, so here A is a pseudo of order 0. So it's given by the integral of the principal symbol of A over the cosphere bundle. So here the cosphere bundle associated, sorry, with the metric G. Okay. All right, so you have these two Fourier spectral triple, and you also have the Tauberian conditions of the main result in terms of zeta functions. So then you get Weyl law for the corresponding Biermann-Schwinger operators. But in this case, what you get, you occur a result of Biermann-Soloniak about the Weyl law for negative order psi-DOs, which can state as follows. So if for any self-adjoint element in the C-star closure of psi 0 of m, you have a Weyl law for the positive and negative eigenvalues of delta g minus n over 4 a delta g to minus n over 4. And I think it should have been, okay, so I know there's a typo here. So it's not n over 4, it's q, it's q. Okay, so I apologize for that. It's not n over 4, it's it should be q. Okay, so it should be q here, I think. Yeah. Sorry about that. So n here should be q, so it's delta g minus q over 4a delta g minus q over 4. And this it's self-adjoint operator, it's positive and negative eigenvalue, it satisfies the Weyl law. So it's like j to the minus q over n times integral of the cosphere bundle of the sum power of the negative or positive part of the principal symbols, and raise this to the power of q over n. Okay. So when q equals n, so again, q equals n, you get j, so you get just a j, so you'll be like j to the minus 1, so it's a weak trace class. And we know that in this case, the Weyl law for positive and negative eigenvalue, the weak trace class implies that you have a trace theorem. So recover that. So we recover the result of Sukochev-Zanin that for all normalized positive trace on L1 infinity. So for all positive normalized positive traces phi on L1 infinity. So for every positive normalized positive trace phi on L1 infinity, phi of a to the phi of a delta g minus n over 2 is equal to the integral of the principal symbols, and this is true for all operator in the C-star closure of phi 0. Okay. All right. So next. 25 until 40. So I still have, okay. So next examples. Okay. So next example is a sub-Riemannian geometry. So this was mentioned. An example of sub-Riemannian manifold is an important example provided by contact manifolds, so mentioned in your talk, and also have a Yakovos also spoke about sub-Riemannian geometry in his talk. And actually, the result of Yakovos presented yesterday will play a role at the end of the talk. So suppose that M is a closed manifold, and H is a subbundle satisfying a bracket condition, which I will explain in a few seconds. And GH is a field of inner product. Okay, H is a bundle. GH is a field of inner product on H. So it's called a sub-Riemannian metric. But in fact, here you can don't necessarily assume H is a subbundle. It's enough to take distributions. But anyway. So the Lie bracket of vector field with value in H gives rise to a chain of distribution in Tn, which are given by taking iterative bracket. So first H1 is H, and H2 is H plus a Lie bracket of vectors with value in H. And you can define this recursively, the other element of the chain. And the bracket condition requires that the chains here is finite. That is, there is R such that HR is equal to Tm. So if you like, it means that at every point, the tangent space is spanned by the bracket of vector fields along H. So a second assumption I will make here, I will explain later how we can relax this. So the equiregularity, so it means that the dimension, so this is a distribution, so it means that, so the HW are distributions, so it means that at each space, for each X, you have a subspace of the tangent space, okay? And it requires the dimension of this subspace to be constant, so they don't depend on X. So in this case, it implies that all the H omega are actually subbundles of T. So there are many examples of sub-Riemannian manifold. So you have a graded nilpotent Lie group. So for instance, Heisenberg group. So I have a nil manifold. So the quotient of graded nilpotent Lie group by lattices, so compact subgroup. Contact manifold is an important example. And this also includes various generalization of contact manifolds. For instance, can take product of contact manifolds. From complex geometry, you have real hypersurfaces in Cn. Those are also examples of sub-Riemannian manifolds. Boundary of symmetric spaces, and you also have numerous examples coming from control theory or applied situations, or real life situations, like when you surf on it gives also an instance of contact structure. Okay, so real life, and all right. So, so in this case, the operator that plays the role of the Laplacian is a sub-Laplacians. So you have a horizontal differentials. So H is contained in H is a subbundle here of Tm. So take its dual, and so you get a defined horizontal differential from smooth function to a section of H star. So that is one form in H star. Okay, so one form dual to H. So simply you apply the usual differential and you restrict to H as a given element of section of H star. And the sub-Laplacians, noted the delta H is simply dH star dH. You have to use, right. So unless H is the whole tangent bundle, the sub-Laplacian is never elliptic because it's always going to miss directions which are in the complement, it's orthogonal to H. Okay. However, thanks to the bracket conditions, there is a well-known result of Hermander, which states that if there were bracket conditions, then the sub-Laplacians, always, as well as associated heat operator, are hypoelliptic. Again, hypoelliptic means that very different notion of hypoellipticity. But what it means is that if delta HU is smooth near a point, then U must be smooth near X. Okay. So in fact, what's even in the paper of Hermander, you have a stronger notion of hypoellipticity in terms of subbundle space estimate. In fact, you can even show that delta H is maximal elliptic as explained in the talk of Yakubos. So in this sub-Riemannian setting, you often require you have another notion of dimensions. So basically, you require the direction in HW, which are not in HW-1, to have weight W. And so you can define a sub-Riemannian dimension as a sum of the W dimension of HW, quotient of HW by HW-1. So that's algebraic. Well, there is some reason for that. So this is, but in fact, the sub-Riemann structure gives rise to it's called Carnot-Carotheodory metric, and the sub-Riemann dimension is also the Hausdorff dimension with respect to this Carnot-Carotheodory metric. All right. So this is this has a geometric meaning, and you have a short-time asymptotic. So this has a long history. So there were, I think, the first result were obtained by Benarous and Rémy Léandre. Also later, so they use, believe, probabilistic method. David Haller used absolute differential method, and also result, more recent result by Colin de Verdière, Hilary, and Trella. So I think, so for equiregular case, Colin, Verdière, Hilary, Trella don't give new result, except they give, they give new result in the sense that they give asymptotic, not just along the kernel, they don't give. So you get this result, short-time asymptotic from the short-time asymptotic of the each kernel. So Colin, Verdière, Hilary, Trella, they give, they also look at the off-diagonal behavior. In a case for our purpose, we only need the diagonal behavior. And what you get is that for every smooth functions, trace of f to the minus t delta h is, and that's not, okay, so I know it's, so d is here is q. So it's like t to the minus q over 2, okay? So that's where also you get here a spectral meaning for the sub-Riemannian dimensions. So the integral of f of some density, some measure. So one part is given by the fundamental solution of the model operator delta hx plus delta t dt on the tangent group gmx at x. So what I mean is that for in this setup, so okay, so I think in this setup, the notion of tangent, the relevant notion of tangent space given by not by a vector space but by a group gmx. So there is process to construct a model operator. So in this case, delta hx is the sub-Laplacians on the tangent group. Okay, and if you take the it operator, you invert it and take the kernel as give fundamental solutions. Currently, it's also given by the it kernel of the model operator, like. And the new, so new edge, this is actually the pop measure. So this is a analog in sub-Riemann geometry of the Riemannian measure. And so you get this right. And so you have this short-term asymptotic. It can be shown that we take a square root of delta h, you get spectral triple, so Q summable. So Q, this is a sub-Riemannian dimension. So you can apply the main result. So you get semiclassical Weyl law, okay, and also get trace theorem. So semiclassical Weyl law say that number negative eigenvalue of h to the 2q delta h q plus v as asymptotic in terms of h to the minus q. Again, q is a sub-Riemann dimension, and with a coefficient which is integral of some power of the negative part of v times so gamma delta h d mu h. Okay. So a difference with Riemannian case is that in Riemannian case you get what you recover is a Riemannian measure. So here you get you don't recover the Riemannian measure, so you don't recover so in the sub-Riemannian case this corresponds to the new edge. You recover a multiple of this you get the measure times some functions, which is given by the gamma delta h. And you also have a trace theorem. That is for every continuous functions and every normalized positive trace phi on L1 infinity, phi of sorry, f delta h minus q over 2 is equal to the integral of f against gamma delta h nu h. Okay. So if you look at the example of a contact manifold, l'avantage of contact manifold is that you can compute everything. So contact manifold, so is a odd-dimensional manifold, which is orientable. Theta is a contact form, so it means that d theta is non-degenerate on a kernel of theta. Kernel of theta plays the role of h. So in this case, Q is 2n plus 2. The tangent space at tangent group at every point is a Heisenberg group. The pop measure is a multiple of the contact volume form, so d theta n wedge theta, and sorry that. And gamma delta h here is a constant. It's equal to gamma n, so yeah, so it's equal to this. So the integral of mu sin mu to the n d mu. So well, you have a similar formula in talks of Yuri. And so you get from that semiclassical Weyl for contact case. So in this case, Q is 2n plus 2, so you get h to the 2n plus 2, number of negative eigenvalue h to q delta hq plus v. So it's one over. So it's some constant times the integral of the negative, some power of the negative part of v against the contact volume, sorry, contact volume measure. And we also have a trace theorem in the sense that if f, so recover trace theorem, so if f is continuous function for every normalized positive trace phi on L1 infinity, phi of f to the delta h to the minus n plus 1 is equal to the integral of f, so some constant, times the integral of f against the contact volume measure. Right. All right, so now I just want to briefly discuss extension to the singular case.
Dear Professor Ponge, you have just 1 minute, actually.
Oh, okay, fine.
Yes.
So you can extend this result to the singular case by using a recent result of Colin-Verdière et Larry-Trilla, which I mentioned before, and result also of Sandro-Lidakis motion in Ken. So this was explained by Jakobos yesterday. So I'll just give one example. Is the Barandy-Grouchin operator on the torus. So we consider, so delta is s squared plus y squared, whereas x is dx. And sorry, typo again, y is 2 1 minus cos x dx. So what's important is that the second vector field is like x squared dx near x equals 0. Okay, so it's not dx, here is y. So sorry about the typo. So it's, yeah, so here the x, so capital X should be y, and dx should be dy. Sorry about that. So distribution generated by x and y is singular on on the Laplace surface x equals 0. Yeah. And you can, so Colin-Verdière and Larry-Trilla, they give an asymptotic in this case, and this the asymptotic, the link term, the it kernel asymptotic, concentrate on the singular set. So what you get is that for every real valued function on the two torus, the limit of h square, h cube, n minus number of negative eigenvalue of h square delta plus v is equal to some constant times the integral over the singular set. So negative part of v, 0y to the 3 alpha dy. Okay. So that's it. Thank you for your attention.
Thank you very much for very interesting talk. So please, if there are any questions, please ask them. Yakovos Androulidakis, please.
Yes, hello. Raphael, thank you for a wonderful talk. I just wanted to ask if you think there might be hope to calculate asymptotics for the Bismuth Laplacian this way, or if you have any thoughts.
Okay, no, I don't have any thought, but okay. It's very good.
Yeah. Thank you, and thank you very much for the talk.
Welcome.
More questions?
May I ask a question? Raphael, I had problems understanding your formula where, so it must be something stupid, where you had the fundamental solution of the Laplacian, and this is just a constant. Could you explain it? I was because it was later on, I think.
Here?
Yeah, right here, right there.
No, because what's happening is okay, so it depends on the convention, but basically the contact manifold is always locally isomorphic to Heisenberg group, so so you have the same thing at every point.
I have something. What? I didn't understand.
Yeah, so well, you have to. So it depends. Okay, so I skip some details. I put some details under the reg, but basically, if you use it depends on the metric you use. But if you use a suitable metric, you're going to get at every point the tangent group is a Heisenberg group, okay? And if you use the metric like suitably, at every point you're going to have the same model operator. And so in the same model operator, you get the same. At every point, the function is constant. So.
Thanks.
So this is I think, yeah.
Professor Rosenblum, do you have questions? We don't hear you. We don't hear you. Please turn on your microphone. Your microphone is not muted by us, not muted, so probably it is not connected. Or you can write in chat. Okay. So, more questions? So let's thank Raphael for a very interesting talk, which connected several groups of researchers, and some of those were present in the audience. This is very interesting. Thank you very much.
Okay, thank you.
Yes, and there is a break now in our